Hello, I'm Sam Wadsworth, and I'm going to be talking about image formation by lenses. So before we talk about lenses, how do we see light? Light functions as a particle and a wave, but when it interacts with different things, it forms light rays, which behave more like particles. A ray is a straight line, so when light hits things and interacts with things like the car in this picture, it does so in straight lines, which are called rays. When light changes mediums, in this example, it goes from air to water. Two things occur. We can have reflection, which is when the air hits the thicker medium, and then it will bounce back at the same angle that it entered. Or you can have refraction, where light rays will go through the medium, and they enter, but they enter at a different angle, called the angle of refraction. Generally speaking, there are two types of lenses. We have convex or convergent lenses, and we have concave or divergent lenses. One easy way to remember this is a concave almost forms a cave in the center. The edges or ends are thicker than the center, and it forms a cave. So concave goes in the middle, and convex is the opposite of that. So here is an image of a concave or divergent lens. Before we talk about image formation, there's a couple key terms that you need to understand. So first, this capital F here on that point stands for the focal point, which is where the light rays seem to emanate from. This little f right here is the distance from the focal point to the center of our lens. So this whole distance here is referred to as the focal length and is represented by the lowercase f. Concave lenses, as we talked about, have the center cave shape, and because of that, they tend to bend light away. Like if you were driving your car along this axis, your outside tires would hit this thicker gravel or snow, and it would pull the car tires away from it. And the same thing happens with light rays. You were going along, and then it pulls the outside first, is what hits the new material, and it pulls the light rays at a different angle away from the axis. Convex lenses are the opposite of the concave lens, but still similar in that the capital F represents the focal point, or the point where the light rays are going to intersect through the lens. The focal length is still represented by the lowercase f, and it still represents the distance from the center of the lens to your focal point. Convex lenses bend light towards the axis, so the opposite of concave lens. A convex lens bends light towards the axis, so that all the rays converge at one point, which is our focal point. So when talking about image formation, one thing we talk about a lot are thin lenses. And by definition, according to OpenStax, a thin lens is defined to be one whose thickness allows rays to refract but does not allow properties such as dispersion and aberrations. So basically what it's saying is we don't want a whole lot of bouncing around inside the lens. We want the light to interact with it and then continue through. And that's what these do. So thin lenses, they have the same focal length on either side, so they're symmetrical. And the parallel light rays entering at a converging lens from the right cross at its focal point on the left, and parallel light rays entering a diverging lens from the right seem to come from the focal point on the right. So with a convex, we have a focal point opposite from the light ray side, and with a concave, we have a focal point that's on the same side as the light rays. One other quick thing to note about thin lenses is that light rays that go through the center, the very middle of a thin lens, is deflected very minimally. So you can assume pretty much zero refraction and problems in ray tracing. So as it goes through, no refraction. It's going to be almost identical, if not identical, as it goes through the center, and only the center of these lenses. So really quickly, for image formation of a lens or by a lens, there are two equations that we use. This first one, 1 over dO plus 1 over di equals 1 over f. dO is distance to your object, di is distance to the image formed by the lens, and as we've already seen, this lowercase f, that represents the focal length of that lens. The second one deals with magnification, where hi is the height of the image that the lens forms. Ho is the height of the object that you are dealing with. And then magnification is also equal to negative di over do. Now, for a converging lens, f, your focal length, will be positive. And for a diverging lens, it will be negative. Di, it's important to remember that di is going to be positive for real images, and di is negative for virtual images. So real images are images formed when there is light, and the image is on the same side as the viewer of the lens. And virtual images are images that appear to have light, but in reality they do not have light, and the image formed is actually on the same side as the object. Convex lenses, or converging lenses, can give two different image formations depending on where the object is. In this scenario, object is here, this woman, and in scenario 1, the distance to the object is greater than the focal length. So when do is greater than focal length, or f, then we will form a positive image. So here's our object, and our image will be formed on the opposite side, right here, giving us a positive and real image. Di is positive, meaning we are going to have a real image. And then to solve for magnification, the height of our image is here and is below the x-axis. So in this case, it would be negative. And ho, or height of our object, is here above the x-axis, giving us a positive. So in this case, our magnification would be a negative number. We would have a negative height of image over a positive height of the object, giving our magnification to be negative. So we would have a positive, real, inverted image. So the other type or scenario that can happen with a convex lens is when the object is closer to the lens than the focal point. So that would mean that our do here, or distance to the object from the lens, center of the lens, is less than the distance from the focal point to the center of the lens. And in this scenario, because of this, we're going to have a virtual image created because our image is actually over here on the same side as where our object is. So the object is here, the rays interact with the lens, and then for the viewer it appears that the the image formed is on the same side as the object. And if we look at our magnification, it gives us the height of the image over the height of the object. And the height of the image is actually going to be greater than the height of our object, giving us a positive and larger magnification. Now with concave lenses, these are unique in the fact that it doesn't matter where the object itself is, the image formed will always be on the same side as the object. So as we look at this, here is our object. This big arrow represents the object in all of these lenses. And it doesn't matter where you place it, the image, the smaller arrow, will always be formed on the same side as the object itself. So we have a image type that would be classified as virtual because it is on the same side as the object, so it's not actually there. And m is going to be positive, although it will be less than 1, meaning that it won't be magnified because the image height is less, this little arrow is less than the big arrow. So a small thing divided by a big thing is still positive, although it's going to be small. So just to summarize the three types of images that we have with these images formed by these lenses. In case 1, we had a positive f because do, distance to our object, was greater than our focal length. So do is greater than f. And we have a real image because the object is on the opposite side as the image. The image comes through on the opposite side, which means that DI is going to be positive because it's on the opposite side, and M is negative because the image formed is below the x-axis while the object is above the x-axis. So we have an inverted image. So this would give us a positive, real, inverted image in case 1. In case 2, when DO is going to be less than the focal length, we have DO, distance to our object, is smaller than the distance to our, or the distance of our focal point. And the image formed is going to be the same side as the object. So here's our image, and here's our object here. They're on the same side, which would give us a virtual image type. And DI is negative because the distance to the image is on the same side as the distance to the object. And then M, the magnification, is going to be positive because the height of the image divided by, so image height divided by the object height. Clearly the image is going to be a lot bigger, so the M is going to be positive and greater than 1. So we have a positive virtual upright image. And then in case 3, with the concave lens, regardless of where our object is, we will always have a negative DI, or distance to the image, because the image is always formed on the same side in all of these, regardless of where the object is. And M is still positive, but it's going to be less than 1 because the height of the image is going to be smaller than the height of the object, or negative DI over DO is going to be still positive, but small. And this gives us, in this case, a negative virtual upright image. And here's just a quick works cited for all the images used in this PowerPoint.